The research paper explores the potential of using K-space data in cardiac MRI for classification, regression, and segmentation tasks. It proposes a transformer-based model, KMAE, which directly processes K-space data without the need for intermediate conversion to the image domain. This model is applied to investigate K-space-based diagnosis in cardiac MRI, comparing its performance with image domain methods like masked autoencoders, MAEs. The results show competitive classification and regression performance, with a myocardium DICE score of 0.884 for segmentation. The model's performance is robust even with 8 times undersampling of the K-space. The authors encourage the MR community to explore the untapped potential of K-space and pursue end-to-end, automated diagnosis with reduced human intervention. In the realm of cardiac magnetic resonance imaging, MRI, leveraging K-space data holds immense potential for various diagnostic tasks such as image reconstruction, segmentation, and the evaluation of flow dynamics and tissue movement. However, undersampled K-space data poses a significant challenge, leading to corrupted or blurred images. To address this issue, the authors propose a transformer-based model called KMAE, which processes complex K-space data efficiently. This model utilizes pre-trained KGIN encoders to attain rich representation and applies different decoders for diverse tasks. The effectiveness of transformers in capturing long-range dependencies and handling complex data structures makes them well suited for modeling temporal dynamics and global information present in K-space data. The paper compares the performance of KMAE with image domain methods, such as masked autoencoders, MAEs, demonstrating competitive classification and regression performance along with satisfactory segmentation results. Overall, the study contributes to the development of a versatile model that can efficiently and accurately diagnose and analyze cardiovascular health using K-space data, highlighting the potential of leveraging complex data in medical imaging. K-space comparative analysis demonstrates robust performance, maintaining consistent results even with 8 times undersampled K-space data. Previous methods for K-space interpolation leveraged auto-calibration signals in the K-space center, with Reiki improving upon these approaches by implementing convolutional neural networks, CNNs. However, these methods did not fully exploit global dependencies present in K-space. Recently, a transformer-based K-space interpolation method considering K-space global dependencies for dynamic cardiac MRI reconstruction was introduced, achieving superior performance compared to baselines. This method's success can be attributed to its ability to model long-range dependencies within K-space, a capability lacking in CNN-based approaches. Downstream tasks, such as cardiac segmentation and motion estimation, have been predicted directly from undersampled dynamic MRI data using CNN-based models. For instance, Schlemper et al. Proposed an end-to-end synthesis network and a latent feature interpolation network, while Küstner et al. Introduced LabNet, which estimates cardiac motion from K-space. Moritz-Rempe et al. Proposed the K-strip model, a complex-valued CNN-based algorithm for skull stripping in MRI. However, these CNN-based methods may not fully exploit global dependencies in K-space. Concurrently, Zhang et al. Proposed using transformers to directly derive segmentation from undersampled K-space data. Inspired by natural language processing, masked image modeling has been adapted to computer vision through vision transformers, VITs. Unlike CNNs, VITs utilize a global self-attention mechanism, allowing for the modeling of long-range dependencies within images. Building upon this concept, masked autoencoders, MAEs, were introduced to extract representations using masked image modeling in a self-supervised manner. KGIN, a K-space representation learning method, was developed based on MAEs to learn K-space representation and conduct cardiac MR reconstruction. KGIN presents robust and superior performance, leveraging its pre-training method that involves processing undersampled K-space data and performing K-space interpolation to predict fully sampled K-space data, which is then converted to MRI via an inverse fast Fourier transform. KGIN model variants, KMAE and MAEs, have been applied to MRI reconstruction and various downstream tasks, including regression, classification, and segmentation. KMAE processes undersampled K-space data, whereas MAEs handle image domain data with masked-out patches. Both models undergo pre-training via K-space interpolation and image reconstruction tasks, achieving high PSNR values that demonstrate the effectiveness of their encoders in extracting meaningful representations from raw data. This pre-training approach significantly reduces training times and facilitates faster adaptation to downstream tasks. For regression and classification tasks, the pre-trained encoder is used to extract valuable feature representations. The architectural framework remains consistent across both KMAE and MAEs. In regression tasks, a pooling layer transforms the extracted features into a feature vector, which is then fed into a fully connected layer to predict the regression value for each subject. For classification tasks, a final layer with a softmax function computes the probability of each class to categorize the subjects. Notably, KMAE and MAEs have been adapted for segmentation tasks, particularly the novel K-space segmentation method. This approach utilizes the decoders of KMAE and MAEs, providing a new approach to segmentation tasks within the MRI domain. The segmentation process in cardiac magnetic resonance (CMR) imaging involves the use of a decoder for image reconstruction in pre-training. For regression and classification tasks, this decoder is removed due to the outputs being numerical values and probabilities. However, for image segmentation tasks, the same reconstruction decoder is adopted. The MAEs process in the image domain and can be adapted for segmentation by replacing the final layer with a sigmoid function. KMAE, on the other hand, handles in the frequency domain, requiring Fourier transfer of the reconstructed K-space to MR images followed by a 1-by-1 convolution layer and a sigmoid function for segmentation. The process is detailed in Figure 1c. The dataset used includes short-axis cardiac MR images from UK Biobank, with corresponding clinical information, and the data is processed to create synthetic K-space data and apply undersampling masks. The dataset is then filtered into three distinct subsets: healthy subgroup, cardiopathy subgroup, and left ventricular dysfunction subgroup, each with specific characteristics for regression and classification tasks. In accelerated cardiac magnetic resonance imaging, selecting the optimal model for regression and classification tasks is crucial. This study presents a comparative analysis of 5 models: ResNet with an acceleration rate of 4, r equals 4, KMAE with r equals 4, and KMAE with r equals 4 but without freezing the encoder. The evaluation metrics employed are mean absolute error for regression and accuracy for classification. The results reveal that the KMAE model with r equals 4 and without freezing the encoder achieves the best performance in both regression and classification tasks, outperforming the other models. This suggests that the KMAE model is more effective at handling undersampled K-space data and improving image reconstruction. Implementation details are also discussed, including pre-training, training strategy, and metrics used. The study utilized an NVIDIA A40 GPU and specific hyperparameters for each model. MRI slices and frames were processed, and ResNet 50 was adapted to handle 2D spatial and temporal dimensions in K-space data. This comprehensive comparison of models for accelerated cardiac magnetic resonance imaging highlights the importance of choosing the appropriate model for achieving optimal results. The findings of this study have significant implications for the development of effective models in this field. The KMAE model outperforms ResNet in regression tasks, showcasing lower mean absolute error (MAE) values for variables like age, left ventricular ejection fraction (LVEF), and left ventricular end diastolic volume, LVEDV. For classification tasks, KMAE achieves higher accuracy than ResNet, regardless of the K-space data sampling rate. Table 2 indicates the transformer model's comparable performance with undersampled K-space data, even when compared to original MRI images. The model's adaptability is evident in the first 2 rows of the table. Even with undersampled K-space data, the model achieves competitive performance, with slight variations compared to full-sampled K-space data. Table 3 shows that MAEs achieves the highest dice coefficient, indicating optimal segmentation performance. KMAE and its undersampled version also exhibit reasonably high dice coefficients, demonstrating accurate segmentation results. Figure 2 illustrates MAEs' optimal segmentation performance by precisely delineating the myocardium within the heart. KMAE employing undersampled K-space inputs also exhibits impressive segmentation capabilities. This study demonstrates the effectiveness of the KMAE model in leveraging K-space data for cardiac imaging analysis, achieving competitive performance even with undersampled data. The KMAE model, introduced by the authors, is a groundbreaking approach that utilizes K-space data for a variety of tasks including disease classification, phenotype regression, and cardiac segmentation. This study showcases the effectiveness of transformer-based architectures in processing K-space data, achieving performance levels comparable to image domain models in both classification and regression tasks. Moreover, the KMAE model demonstrates robustness and maintains consistent performance even with undersampled K-space data, highlighting its potential for accelerated MRI applications. The transformer architecture excels at handling global information in K-space, efficiently capturing correlations between diverse positions. In cardiac applications, the model processes K-space frames as time sequences, integrating temporal information by segmenting frames into patches. This allows for the capture of cardiac dynamics over time. Results from undersampled K-space data outperform those from fully sampled K-space, suggesting that the former focuses more on low-frequency components, which are crucial for downstream tasks. Predictions based on MAEs for fully sampled images represent the upper bound of performance comparison, underscoring the potential for direct application in K-space-based diagnostics and cardiac assessment. Future work will extend this method to multi-coil CMR scans, enabling the incorporation of more redundant information and further improving estimation accuracy compared to image domain-based methods. This research underscores the considerable promise of employing K-space data in cardiac MRI and confirms the suitability of transformer architectures for this purpose. The authors conclude their comparative analysis of K-space architectures for cardiac MRI scans, highlighting the potential for future research to extend to multi-coil CMR scans and explore further downstream tasks to validate and expand these findings in clinical settings. The authors acknowledge the use of the UK Biobank resource under application number 87802 and funding from the European Research Council (ERC) project DEEP-4MI 884,622. They declare no competing interests relevant to the content of this article. In the realm of medical imaging, particularly magnetic resonance imaging (MRI), recent research papers have introduced significant advancements in reconstruction techniques. These include self-supervised motion-corrected image reconstruction networks and non-rigid registration derived in K-space. Accurate segmentation is also a critical aspect, with novel algorithms for skull stripping and cardiac MR segmentation being developed. Moreover, deep learning techniques are being applied to disease classification and localization on chest X-ray. This summary aims to provide a comprehensive overview of the latest developments in medical imaging, bridging the gap between research and practical applications. This page presents a comparative analysis of the proposed method in K-space, leveraging variational networks for accelerated MRI reconstruction. The authors draw parallels with existing works, including Sriram et al. 2020, and Zhang et al. 2024, to contextualize their approach. The referenced paper by Sriram et al. 2020 introduces end-to-end variational networks for accelerated MRI reconstruction, demonstrating the potential of deep learning-based methods in this domain. In contrast, Zhang et al. 2024 focus on whole-heart 3D plus T representation learning through sparse 2D cardiac MR images, showcasing the efficacy of transformer-based architectures in cardiac image analysis. Another relevant work by Zhang et al. 2024 explores direct cardiac segmentation from undersampled K-space using transformers, highlighting the feasibility of leveraging K-space data for cardiac segmentation tasks. The comparative analysis in this study aims to investigate the performance of the proposed method in K-space, benchmarking it against these existing approaches. By examining the strengths and limitations of each method, The authors provide a comprehensive understanding of the current state of the art in accelerated MRI reconstruction and cardiac image analysis using K-space data. This comparative analysis facilitates a nuanced evaluation of the proposed method's contributions and potential applications in the field.